Assalamu alaikum and welcome again our ISA Oman section viewer and audiences. We are happy to host you again in this Knowledge Connect from ISA Oman. We hear your request. I know some people contacted me and they are saying, we've been only hearing about OT cybersecurity. We want to know more about control automation. We want to hear more about control automation. And that's why I'm introducing and welcoming our host for this today's session, Ms. Pretty Zaid, IC Oman section webmaster. Welcome on board, Pretty.
Thank you, Nasser. Thank you for having me here.
So from now on, Pretty will be hosting control automation sessions, and uh, I think she will welcome our host or our guest speaker for today. I'll leave the floor to you, Pretty. Take care.
Thank you, Nasser. Yeah, thank you. Hello, everyone. Assalamu alaikum, and welcome to another session of the ISA Knowledge Connect series. Today, we are honored to spotlight a young and promising talent in the field of engineering and innovation. It is my pleasure to introduce Mr. Mohammed AlBadi, a fresh graduate in electrical engineering, instrumentation and control from very renowned university, that is Sultan Qaboos University. Mohammed is a part of the next generation of engineers who are bringing fresh perspective, advanced technical skills, and innovative thinking to our industry. During his academic journey, Mohammed demonstrated a strong passion for automation, control systems, and emerging technologies. His commitment to continuous learning and hands on exploration is reflected in his project we will present it today, an excellent showcase of applied engineering in the rapidly evolving domain. Today, Mohammed will be discussing his final year project titled Design and Implementation of Software Defined Radio (SDR) Communication System for CubeSats. This project addresses one of the most exciting frontiers in the modern engineering, space communication technologies. His work explores how software defined radio can be leveraged to enhance communication capabilities for CubeSats, with small but powerful satellites transforming the space industry. We are excited to hear more about his design process, implementation challenges, and the innovation embedded in his solution. Please join me welcoming Mr. Mohammed Al Badi to the virtual stage. Welcome on board, Mohammed.
Thank you, Ms. Pretty, and thank you very much for Isa Aman for giving me this opportunity to speak today. And it really means a lot to me, especially as a fresh graduate, to be able to share about my project with such an inspiring community like ISA Oman. And I hope you find it informative and enjoyable, inshallah.
Yes, I know, like me, everybody, our viewer must be excited for today's session. Before we jump on to the presentation, if you don't mind, I would like to ask you a question. Why did you choose this topic as your final year project?
Yeah, actually, I know this is a challenging topic, but like from very young age, I have always been passionate about space and learning about these new technologies. So I go ahead and see how it goes. It's really interesting topic, so I went to it. Yeah.
Okay, so it's astrophysics, astronomy, quantum physics. Thanks.
Communication.
Let's jump on to the presentation now. The floor is yours.
Okay. Thank you very much, Miss Pretty. So, Bismillah ar-Rahman ar-Rahim. Assalamu alaikum wa rahmatullahi wa barakatuh. In today's talk, I will be talking about design and implementation of a software-defined radio SDR communication system for CubeSat. And that was my final year project in Sultan Qaboos University. In today's talk, I will be talking about these topics. First, I will introduce an introduction where I will present about the satellites and CubeSat, then the problem statement where I will also introduce the solution that we propose then the objectives of the project requirements, the system design, and why did we choose its different parts, then into the implementation, the results, and finally, I will conclude with the conclusion and the future work. Now, when we think about satellites, the first picture that often comes to our mind are these huge and gigantic structures orbiting the Earth, weighing several tons and costing millions or even billions of dollars to develop and to deploy into space. Well, those are actually called traditional satellite. And one example of those is the Intelsat 35E, a communication satellite that have a dimension like a school, as equal like a school bus, and also it weighs around 7 tons and have cost around 400 million US dollar, including the development cost and the deployment cost, since it needed a dedicated launcher, SpaceX Falcon 9 rocket in 2017. Now imagine if you can minimize this technology to a size that is slightly bigger than a Rubik cube, and at the same time make this technology accessible and cost effective. And you will end up with what we call CubeSat. Now, in technical terms, a CubeSat is a type of nano satellites that uses a unit form factor of U, where one unit or one U is 10 centimeters in each dimension. Also, for one unit CubeSat, the weight cannot exceed 1.33 kilograms. Also, in general, for CubeSat, the development and the deployment cost can be less than 150,000 US dollars, since these CubeSat are typically launched as a secondary payload on a larger missions. Now, having this clear standard that defines the weight and the size have led to cheaper development and deployment, as we have discussed. However, having smaller size means smaller space for solar panels and also smaller batteries, and that would ultimately affect the payload capability. Furthermore, using traditional hard fixed radios lack the flexibility that's needed for space, especially for the space harsh environment. So, to solve these problems, we have proposed to use of the technology that's called software-defined radio or SDR. Now, the next logical question that comes to mind is what is an SDR? Now, an SDR is a radio communication system where signal processing is performed in software instead of hardware. So all the different communication parameters like the central frequency, the modulation technique, the cutoff frequency for the filters, all of these parameters you can change in software instead of relying on hardware adjustment as in the case of hardware radios. Some advantages of SDR in CubeSat is that they allows for adaptive communication system, as we have discussed, and also it offers a cost-effective solution. Here, when we say cost-effective, we mainly aim in the cost of the testing before the actual deployment. Here's a little comparison between traditional radios and SDR radios for CubeSat mission in terms of three aspects. The flexibility and adaptability, we can easily say that SDR can be updated with the new softwares even after the deployment into space, whereas hardware radios are static. In terms of test cost and launch readiness, SDR has a lower cost and also faster preparation time, whereas for the hardware radios, you would need to spend more money for testing many models. In the case of the protocol support, SDR can support a wide range of protocols and also adapt to new protocols after the deployment, whereas hard radios are limited to specific protocols and lack the flexibility. Moving forward to the objectives of our project, we aim to have two objectives. The first one, we wish to explore how space communication can be enhanced using the technology of SDR. The second objective is that we wish to investigate and implement an SDR technology in the CubeSat. We would make this possible by implementing a prototype of a CubeSat to ground station communication link. Now, the first stage in the for any CubeSat subsystem is by starting with the design constraint. Now for CubeSat have very limited power. Usually this power is less than 2 watts for the communication electronics. Furthermore, when we wish to use a frequency, our chosen frequency must align with the ITU regulation, since the space communication is regulated. And finally, we must respect the hardware form factor of the SDR, and also the system should connect with a USB with the computer that we will use. Now we have converted these this specification into those engineering requirements, and those engineering requirements are important since we can use them at the end of the implementation in order to validate whether we have successfully achieved the objectives of the project or not. So we have around 5 engineering requirements here. The cost of the system should be less than 200 Omani riyals. The second requirement is the frequency that we will use. It should be 3 gigahertz, and this frequency aligns with the antenna group frequency, since, as you may know, our project was not working all alone. It was working with different CubeSat FYB groups in Sultan Qaboos University, and our group was responsible for the communication channel. Now, for the third engineering requirement is the operating voltage, and this also aligns with the electrical power supply of the EBC CubeSat FYB group, and we have targeted to be 3.3 volt to 5 volt. Now, for the dimension and the weight, it also must align with the restriction of the CubeSat. So the dimension is less than 9 times 9 times 3 centimeters model. And also for the weight, it should be less than 130 grams. Moving forward to the system design and integration. Now, for our design, we have to choose two main things. We have to choose the hardware SDR and also the software that would define the communication parameter of the hardware. Now for our project, we have prioritized to start with the software first. Now we have started with several criteria like the cost, the ease of use, the hardware compatibility, and the performance. And we have seen 3 different alternatives, 3 different software: MATLAB, GNU Radio, and LabVIEW. Now, to compare between those alternatives, we have used the method analytical hierarchy process, a method to compare between those alternatives, and ultimately we have found that we would use GNU Radio as the software for our project. Now, the second thing to choose or to consider is the hardware choice. Now, to reduce the cost, we have decided to look into the existing software hardware models that exist in Sultan Qaboos University. The first model that we have looked into is Emona TIMS 451 SDR, and this model was a little old, and also it was GNU Radio incompatible, so we would not use this one. The second model that we have looked into was NI-USRP 2920. This have very good performance. However, it is bigger than the requirements, so also we would not use this one. The third model is the one that we have decided to choose since it is compact and also it is GNU Radio supported. So we will use this one, which is CS Lime 05 crowded supply. So in summary, for our system, we will utilize GNU Radio as the software, and also we will utilize Lime SDR as the hardware for our project. Now into the implementation. For our implementation, we started our implementation journey by following a logical building manner, starting from from a software-based simulation into the actual hardware building. So we have implemented around 3 implementation scenario. Now the first implementation scenario is the one that you can see here, is the back-to-back simulation, where we implement the transmitter and the receiver both in the same computer, and we send and receive the message without the use of the hardware. This is important to validate and test the channel through the software. Now the second implementation scenario is the loop back using one SDR, where we send and receive through the SDR to the air back to the same SDR, and this is important to validate and test the over-the-air transmission for the system. The third implementation scenario is the unidirectional link, where we have used 2 SDRs, one SDR attached to one computer. And this implementation simulates a prototype for a CubeSat to ground station link, which is our ultimate goal. Now, to be able to understand the implementation itself, we would first need to look into this simplified communication link for space to ground station communication. For space to ground communication, we start with a payload data. This data can be a reading from a sensor or a picture that the satellite have taken. Then we packet frame this data. Then we modulate this data to allow it to be transmitted for long distances through the channel. Then at the other end, we filter out the noise, we demodulate the data, then we packet deframe it, and finally we receive it in the ground station. Now moving forward, this is the first implementation. This is the GNU radio that we have implemented. This is the first implementation scenario, the back-to-back simulation. Here we can see there are a few or many things actually, but we would focus on the main parameters. Here are 3 main things here. The simulation parameters. We have a variable that define the sample rate that we will use. We have set it to 500 kilosample per second. The second thing is the transmitter chain. We will start from the left to the right. Now for the transmitter, we have a file source that acquires the data from the computer. Here the data is a text file. We have named it as txt.txt. Then we packet frame this data using a packet encoder. Then we modulate the data using GMSK modulation technique. So this is the Gaussian minimum shift keying modulation technique, and it is a widely used communication technique for space missions, and it's also used for communication. Now moving forward in the chain, we have a throttle that restricts the system to run at the sample rate, 500 kilosample per second, and at the very end of the chain, we have Qt GUI sync in order to visualize the signal, and we also have a virtual sync to connect the chain to the receiver. Now, implementing this implementation, we can have a data rate of 125 kilobits per second. And we can easily change this as required, but I will not go into these details now. All what we need to know is that we have this data rate. Now moving to the third main thing here is the receiver. Starting from the left side, we have a virtual source disconnect from the transmitter. We have multiplied by a constant. This value we can increase the signal if needed. Then we have a low pass filter to filter out the noise. We demodulate using the same modulation scheme, GMSK here demodulation. we packet decode using the packet decoder, and finally we save the data in the computer using file sync, and we save it as rx.txt. So we save it as a text file. So this is pretty much the whole implementation for the back-to-back simulation, the first implementation. Now for the other two implementation, they would be pretty much the same, but with few differences. These differences will be because we have introduced the hardware. So the noticeable differences is that for the transmitter, we introduce a new variable that defines the central frequency. We have set it to 3 gigahertz. Now for the transmitter, we have replaced the virtual sync by Lime Suit Sync TX, which allow the use of the SDR to send the signals. Now for the receiver, we have replaced the virtual source by Lime Suit Source RX to allow the SDR to capture the radio frequency signals into the system. And this is pretty much the whole loop back with one SDR. Now for the third implementation scenario, it would be exactly the same as the previous one. However, the only difference that we will separate the transmitter and put it in one computer, and the receiver blocks, and we will put them in another computer, and we will attach one SDR in each computer. Now for the hardware setup, here I'm just mentioning the components, the hardware that we will use for the back-to-back. We'll utilize one computer, the loop back, one computer, one SDR. For the unidirectional links, 2 computers and 2 SDRs. This slide is pretty much a repetition of what I have mentioned. The noticeable thing here for the unidirectional link, we will utilize a Raspberry Pi instead of a personal computer in order to have a compact size. Now moving forward to the results. Now for the first implementation scenario, the result is very straightforward. We only have a text file we transmit this text file, and we receive the text file also in the same computer. This is without any hardware. Now for the second implementation scenario, the loop back using one SDR. Now here you can see the file on the left has the message that we will send. It's a text message that says loop back using one SDR, and the file on the right is where we will save the file after we receive the file. Now I will run the video. Now I will go ahead and run the flow graph. As you can see here, now here the signal for the transmitter and the receiver, they both look the same. And here in the receiver, we have get the same text as the transmitted text, as you can see in the slide here. So this was the loopback where we have used one computer and one SDR. Now moving forward for the third implementation scenario, the unidirectional link. Here you can see the ground station where it's initially listening with no signal. The signal that you can see here is the noise signal. Now I will run the video. And now I will go ahead to the CubeSat and run the flow graph to send the message. Here we also have the signal, the transmitted signal, and also I am sending a text message that says data from the CubeSat, as you can see in the presentation here. Now to the ground station, we can say that we have the same signal as the transmitted one, and also we get the same text as you can see here in the slide. And this shows that we have been able to send and receive using the 2 SDRs. Now furthermore, we have implemented another test, but instead of using text message, we have transmitted a picture instead of text. So we have inserted this picture into the loopback system, and we have get this result as you can see in the slide here. So the picture on the left, in the right side, is the received one, and you can clearly see that we have some pixels that were missing from the picture. And after looking through this problem, we have seen that this is because we did not implemented forward error correction, and by the proper implementation of forward error correction, we can have a system that can transmit pictures. Now to the conclusion. To conclude, we have successfully designed and tested a basic SDR communication system for CubeSat. We have implemented a prototype that works well for text transmission. However, when uh, we have observed some limitation like packet drops and no error correction. So for the future work, we can implement a forward error correction, which would allow for image sending system, and then we can test the system with the real antennas, and finally we can integrate this whole system into a CubeSat onboard computer, and hopefully one day we can see this project in the space. And with that, we reach to the end of our presentation. Thank you very much for listening, and please feel free to ask any question in mind.
Thank you, Mohammed. It was
Thank you.
really informative. So, on behalf of ISA Oman section, we would like to extend our sincere appreciation to Mr. Mohammed AlBadi for his excellent and inspiring presentation on design and implementation of a software-defined radio (SDR) communication system for CubeSats. Today's session truly showcased the power of young talent, innovation, and practical engineering application. Mohammad's work reflects not only strong technical capability, but also the importance of academic research in supporting future technologies such as space system, satellite communication, and advanced control and communication platform. We are proud to see such high quality work coming from Sultan Qaboos University, and we look forward to seeing Mohammad's continued success and contribution to the engineering and technology sector. Thank you again, Mohammed, for this knowledge sharing section.
Thank you very much, Pretty. Thank you.
Now, would like to get some questions from our viewers. So the
Yes, sure.
first one, yeah, are you ready?
Yes.
Yeah. So the first question is you selected GNU radio using the HP method. If this system were deployed on an actual CubeSat mission, would your software selection criteria or weight changes?
Yes, absolutely. For real CubeSat mission, I would we would often of the time choose the hardware constraints first, and then move to the software. But for our project, we inverted this flow to save time and also to focus on the rapid prototype development. So in real project, we would choose the hardware first and then move into the software.
Okay. We have another question. If you were to continue this project professionally, what would be the next major improvement you would prioritize in this project?
If I would to continue this project, I would prioritize the link budget analysis first, and also the forward error correction and the test for the system with real antennas to move this prototype to a mission ready system at the end.
Yeah, the cost effective approach surely will help. We
Yeah.
have another question coming in from a viewer. Now, how scalable is your current implementation if a higher data rates or more complex payloads are required?
Okay, now for our implementation, the architecture is scalable, but in the software level only. But for real real project, the scalability would require a link budget optimization and also better hardware. We would need to have some better SDR units, and also we might need some adaptive modulation and coding, and maybe also use some the use of some defined protocols in order to scale it and to have it for complex payloads.
Thank you very much, Mohammed, for this session. It was really knowledgeable and very much curious to know more. I'm
Thank you very
sure
much.
for our young students must have taken a lot from today's presentation. They may be curious to know more about this topic. Thank you very much.
Thank you very much, Pretty, and thank you very much for Isa, man. Thank you.
So, before we conclude today's session, we would like to encourage all attendees, especially students and young professionals, to register as a member of ISA and join ISA Oman section. ISA membership provides global access to the automation and instrumentation standards, technical libraries, tools, and publication, training programs and professional certifications, webinars, workshops, and industry networking sector. Career development supports students, graduates, and professionals. Whether you are setting your career or advancing in automation control, OT, or cybersecurity, ISA empowers your professional journey. We are here to take care of it. Thank you all again and see you soon, our future ISA Oman Knowledge Connect section. Have a safe and wonderful day ahead.